Okay, we can get started. Any questions? So let me remind you that what we did last time was I formulated the large sieve, which was an inequality for this exponential sum and then the bound that we had was that if you sum over values, m goes from 1 to m, and the alpha j's are delta space, so any two of them differ by at least delta in distance taken mod 1. Then there's a bound for this that we proved. It was bounded by something like n plus big O of 1 over delta times the average of these coefficients, sum over n. Right? And we proved basically a couple of different versions of this result. None of them actually as precise as this, but with the less than, I gave a couple of proofs. Let me also make one more observation. In this sum, I could also start, if you like, with the interval from k plus 1 to k plus n of a n e of n alpha. Right? In other words, I don't have to imagine that these first n parameters, what I'm plugging in here, that these are starting in the initial interval. And the reason for this is that I could just replace n by k plus n, if you like, and then just this constant phase comes out. Okay? And this makes no difference. And then I would have exactly the same bound with the sum over n, with the same n here being the length of the interval, doesn't depend on where the endpoints of the interval are, and then you would get the same quantity here. Is this okay? Okay. So this is the large sieve, and in applications, we usually have in mind some special sequence of points. So let me give an example of this, is that I can fix a number q and take alpha j to be all reduced fractions in 0 to 1 with denominator less than q. Okay, so in other words, I'm looking at a sum over q up to q, and then a sum over all reduced residue classes a mod q. So I'm going to put a star here to indicate that a is co-prime to q. And then I'm going to evaluate this exponential sum at the fraction a over q. Right? If I take two fractions with denominator less than q and they are not the same, then the difference between them is a fraction with denominator, the product of the two denominators. Right? Maybe there's some cancellation with the numerator, but at least it has that fraction, at most that fraction q squared in the denominator. So these numbers, these reduced fractions, are all 1 over q squared separated from each other. So delta would be like 1 over q squared. And then the large sieve gives me a bound of something like n plus big O of q squared times the sum mod a n squared. Okay. So this is the form of the large sieve that we will use. And let me point out that that this form will help you see why the large sieve is a sieve. So to give an application of this, let me return to my problem of counting the number of primes in an interval from x to x plus y. This is the Brun-Titchmarsh theorem that we proved using the Selberg sieve a couple of days back. So let's bound this using the large sieve instead. So I'm going to take my function S alpha to be the sum over, say, n is a prime, p goes from x to x plus y, e of p alpha. Okay. And then the large sieve is telling me some bound that this sum over q up to some size capital Q, then the sum over a co-prime to q, s of a over q, that this is bounded by, so n is played by y. So this is why I said that you can translate that interval in S alpha by anything that you like. It doesn't depend upon what the numbers actually are, just on the length of the interval that you're in. So this is a y plus q squared times, well, what's an? It's 1 if your number is a prime and 0 otherwise. So the sum of the squares of that will again give me pi x plus y minus pi x. Right? So that's an upper bound. Okay, upper bound for something. Right? So an upper bound for what? Well, let's examine each one of these. So how big should this quantity be? Okay, so I don't know how big this quantity should be. Let me, for example, think about just the average of this, the sum over a mod q. So I sum over the reduced fractions with denominator q, right, of this exponential sum. Well, what is that? That's the same as if I sum here, it's a sum over p between x and x plus y. You can see from this that I'm going to choose my capital Q to be a little bit smaller than root y. Okay, so that this term will be negligible compared to this main term. Okay, so then if I sum this inner sum here, E of P A over Q, over all reduced fractions A mod Q, P is a prime, it's going to be co-prime to this number Q. Okay, A is co-prime to the number Q, so I'm summing over all the primitive Qth roots of unity. Right? And the sum over the primitive Qth roots of unity is something called the Ramanujan sum. So this would be the Ramanujan sum of to the modulus Q of P, something like that. Now, it's an elementary exercise to check that if you want to compute this Ramanujan sum, you would get an answer that this is exactly equal to the Möbius function of Q. If you sum all the primitive roots of Qth roots of unity, you get the Möbius function of Q. Okay? So then this would be the Möbius function of Q times the number of primes in my interval. But that means that if I use Cauchy-Schwarz, so if I use Cauchy-Schwarz, then I get that so Cauchy-Schwarz would say that this is bounded by, well, the sum over A mod Q of 1 squared, which is phi of Q, times the sum over A mod Q of which is the quantity that's being bounded in the large sieve, right? So this is, what did we say? So this is mu of Q times pi x plus y minus pi x. So this quantity is at least as large as this quantity squared, which is mu of Q squared, divided by that, which is phi of Q, times pi of x plus y quantity squared. Right? And so if I now plug that into the large sieve, so if I input that into the large sieve, I get pi of x, thanks, times the sum over Q up to Q that this is bounded by y plus big O of Q squared times pi of x plus y minus pi of x. Right? Or if I cancel one of these quantities and divide by that quantity, I get an upper bound for the number of primes on this interval from x to x plus y. Okay. What do you notice about this upper bound? Yeah?
It's almost comparable to the prime number theorem bound. The only problem is for summing reciprocals to prime, not reciprocals of all numbers up to Q.
I'm actually summing over all reciprocals of all numbers up to Q. Q doesn't have to be a prime. Right? So in fact, yeah. So in fact, this quantity would be of size log of capital Q. I should choose Q to be of size square root of y, and then I get a bound which is like y divided by log of y with a constant 2. Right? Yeah? The sum over Q is exactly the same thing, right? Not even a little bit different. It's exactly the same thing that shows up in Selberg sieve. Okay? So the large sieve is in some ways closely related to Selberg sieve. Nice and Selberg sieve. And maybe, if someone wants, this might be yet another project to think about, which is why do you get the same answer in the large sieve and the Selberg sieve? And there are some old papers that I can give references to which deal with this. Okay. Now, another way, so let me say make one more point about the large sieve. This I won't work out, but you can try to work out. So the large sieve gives you some upper bound for this exponential sum on average, right? Now, what does it mean for this exponential sum on average to be, so it's telling you that this exponential sum is small, okay? So, but what is the exponential sum doing? It's the value at a over q, so it's taking all your numbers, weighting them with different roots of unity, right? So if you have a sequence which is equally distributed in every arithmetic progression, then you would get all the roots of unity adding up, and the roots of unity will all add up to 0, because if you sum over a complete set of roots of unity, you get 0, right? On the other hand, if your sequence is not equally distributed in every progression, then you might expect that some roots of unity are favored over others, and that you don't have cancellation, right? This is in fact what happens for the primes in this argument, because the primes do not occupy all the residue classes evenly, they miss the ones that are divisible by some prime. They occupy only the reduced residue classes. Yeah? And that's what we exploited here in order to get our upper bound for the number of primes in an interval. Okay? So similarly, you can formulate this from this analytic inequality, you can give an upper bound for so an being the characteristic function of a sequence, and suppose the sequence which, so you're given a sequence which occupies, or let's say which avoids some number nu of p residue classes mod p for each prime p. Okay? So for example, the sequence of primes, you would say that nu of p would be 1, because the sequence of primes avoids one residue class mod p for each prime p, namely the residue class 0 mod p. So if you think of the Hardy-Littlewood k-tuple problem, where you want n plus h1 to n plus hk all to be prime, then for each prime, you're avoiding the residue classes minus h1, minus h2, minus h3 up to minus hk. So the number of distinct elements in your set H, in your admissible set H, let's say, mod P. Okay? So if you know this, then that sequence cannot be evenly distributed in every progression. So therefore, the exponential sum you expect to be somewhat big on average, and then you can plug that back into the large sieve and get an estimate for the number of elements in your sequence. This is good in principle. You should carry out this kind of as an exercise. It would be exactly like what we worked out here, just that you have to use extra information about what this new P is telling you. Okay? So in this way, you can think of, there are other situations where the large sieve is quite powerful. So for example, if you have a sequence with nu P is at least, say, P minus 1 over 2, so something quite big, you're omitting quite a few residue classes mod P for each prime P, then the large sieve would say that if you have such a sequence A, then the number of elements in your sequence A up to n would be bounded by something like square root of n. Okay? So it's kind of remarkable that it's a remarkable bound, because it shows that there are, if you have to avoid many residue classes, it shows that there are very few elements in your sequence, right? But maybe it's not remarkable enough, because you might say, okay, so for each prime P, there's like a chance of a 50% chance that you will succeed in avoiding 50% of the primes mod p, right? But there are lots of primes. So if you have to do this for 2 and 3, maybe there's a quarter chance of avoiding both of them. Yeah? But you can keep doing this for all the primes, and there are lots of primes. So you would think that actually extremely, not even square root of n, you should think that nothing should be able to avoid half the residue classes mod p for each prime p. Right? It seems miraculous that such a thing should exist, but it does exist. For example, the squares satisfy that. Okay? If you take a square and you reduce it mod p, then what you get must be either 0 or a quadratic residue. So you're avoiding p minus 1 over 2 residue classes, namely the quadratic non-residues mod p. And then the number of elements that are squares up to n is exactly square root of n. Right? So this is optimal in a certain sense by thinking of the squares. So the large sieve is great because it kind of captures this, this very algebraic example of the squares. But you could ask for more. So suppose or another way to say it is that, can you think of examples besides the squares where there are as many elements as like square root of n? You can tweak the squares a bit, n squared plus 1 or n squared plus 3n plus 5 or whatever, right? You could then start playing around with cubic polynomials, but cubic polynomials is not so easy because there will be some primes for which maybe it will represent all residue classes mod p, right? Anyway, you can think of trying to construct with other examples of the situation where some large number of residue classes are omitted, and then the set itself still happens to be large. Okay, and there's kind of a vague conjecture that any such example like that should come in some way from an algebraic reason, like taking a polynomial values or some generalization of that. Okay, and if you don't have some algebraic structure, then you should be able to do better than that. And we don't really have any good understanding of these kinds of questions on the large sieve. So I'll just give you a couple of references to think through. There's work of Helfgott and Venkatesh. And also by Green and Harper. And also some work by Miguel Walsh and also Fernando Shao. And all of these, so if you Google or search for papers and search for something like inverse large sieve, you'll find these references, and they're trying to understand, what other large sets that you can have which are concentrated on a small number of residue classes, mod p, either for each prime p or most primes p or some version. Okay, so that's a bit of a digression. So let me get back to the large sieve and its applications to the Bombieri-Vinogradov theorem. So I want to use something like the large sieve to understand primes and progressions. So now I'm going to proceed from the additive formulation of the large sieve as an inequality for these exponential sums. I want to go from here to formulating the large sieve for multiplicative characters. So again, I'm going to assume that I'm given some arbitrary numbers an, and I'm going to be interested in, now let me call this S of chi to be the sum of an chi n. And what I'm going to be after is a bound over of the following form. I'm going to sum over all moduli q up to q, and then sum over all the characters chi mod q, and then sum something like s of chi squared. And then I want a bound for this in terms of the sum over all n a n squared. Okay? So this is a little bit like this inequality that we wrote down here. Right? Now, notice that in this inequality, we made sure that we didn't sum over all the fractions a mod q, a over q, but only the fractions that were reduced, right? And the reason for that is, of course, that I don't want to count half many, many times as half, 2 over 4, 3 over 6, etc., right? Otherwise, I'll be counting the same fraction many, many times. And what was important was that these fractions were all well spaced from each other so that the exponential sum genuinely behaved differently on different fractions. Okay? So I want to do the same thing here. I want to make sure that I don't count the same character many, many times. And now, this you would have seen from Dimitri's lectures. So the characters, if you have a character mod 4, you might as well think of it as a character mod 8 by just pretending that it's periodic mod 8 when in fact it was periodic mod 4. So that's the notion of an imprimitive character. And you want to make sure that you don't want to count the same character many, many times, like with fractions. So we only want to count here over the primitive characters chi. So this star that the characters are primitive. That's fine. So there are about q squared characters that are being counted here, and they're all distinct from each other. Right? So maybe there's a small exercise that's in order. You might want to think about, well, firstly, how many characters are there mod q? This you did go through. Phi of q, yeah. And then how many of these are primitive characters mod q? Is that right? Phi of q? Okay, let's think of this. How many characters are the modulo prime p? So there are p minus 1 characters mod p, right? But how many of them are primitive? So there's only one character which is not primitive, namely the character that's trivial all the time, right? And then p minus 2 of them are in fact primitive. So it's not phi of p minus 1. Okay? So I think what you're thinking of is the number of primitive roots mod p, which is phi of p minus 1. Okay? But the number of primitive characters is just p minus 2. And then it's just multiplicative. So it's basically like the product of p minus 2 over all the primes p that divide your number q, and not p minus 1. Okay, so anyway, there are about q guys that are being counted here. So the total number of guys that are being counted here is some constant times q squared. Okay? And again, our expectation should be that there is one bad guy, one bad character, for which this could all of these could be pointing in the same direction, in which case you should get n times the sum of mod a n squared. So that's one object. And then there could be something like the rest of them, the rest of the q squared objects, there should be square root cancellation. So in other words, bounded by this on average. And so a bound of the form big O of q squared. Okay? So that's the large sieve in its multiplicative form. What's the constant? For what? Probably 1. Yeah. Right? Yeah, you could say it's 1. In fact, it's even a little bit better because I can even put in something a little bigger than 1 here. We'll see, right, what it Okay, so that's what I'm going to aim for. And the proof of this is not very hard. It's basically it involves a change from going from multiplicative characters to additive characters. I'm going to reduce this. I'm going to prove this by reducing to the additive case. Okay, so Demetrius kind of told you how to do this. So you can think of the additive characters, the exponentials. They form a basis for all the functions that live on Z mod QZ. Right? You can decompose them in terms of additive characters. And then the multiplicative characters give you a similar decomposition of all the functions that live on Z mod QZ star. Right? But the orthogonality relations allow you to pick any function that you want on Z mod QZ star using multiplicative characters. And then you can ask, you have one basis and you have another basis. You can ask, how do you write terms in your base in one basis in terms of your other basis, right? And this is the formula that he worked out. If chi is primitive, this works particularly nicely. So recall from Demetrius's lectures that you can understand chi n. Okay, I can never get this proof somehow right, so I'm going to write down the thing, and then we'll work out what it means. So suppose I start out by looking at chi of a n e of a n over q. Well, let me just start with this. Chi of n e of a n over q, right? And then if I multiply and divide by chi of a, so that's the same thing, at least if n is coprime to q, okay? And then this guy is the Gauss sum that was defined by Demetrius. If n is coprime to q, then if a runs over all the residue classes mod q, then so does an. So this is just the sum of chi n e of n over q. So this is chi bar of n times tau chi. Okay? So if I rearrange this a little bit, what I get is that, and take complex conjugates everywhere, then chi of n is 1 over tau of chi bar times the sum over a mod q, chi bar of a e of a n over q. This is, what did Demetrius call this? Conjugate eigenvector for chi. This okay? Right? So I just use this formula, replacing chi here with chi bar, and then divide by the other side. Right? And here recall that the size of the Gauss sum tau chi is square root of q. Right? And so the proof that I gave here is true for if n is coprime to q, but what Demetrius proved to you was that if chi is a primitive character, then this relation is true whether n is coprime to q or not. So this is valid for all n. If chi is primitive. Okay. Okay, so this relation allows me to pass from my sum for over characters s chi to the corresponding sum over exponential functions, over the exponential sums. So this is the sum of an chi n, which by our relation is 1 over tau chi an, and then a sum over maybe I shouldn't have used a, so let's say sum over b mod q chi bar of b e of bn over q, which is the sum 1 over tau chi bar sum over b mod q chi bar of b. And let me just call this exponential sum with the same s, but realizing that this is an exponential sum b over q. So far, so good? Okay. So all I've done is pass from the sum over characters to, by a change of basis, to the exponential sums, linear combination of exponential sums. So therefore, if I now sum over all the primitive characters chi mod q, well, for primitive characters, the size of the Gauss sum is root q. So if I square this, I get 1 over q, and then a sum again over primitive characters chi. Square. But now at this stage, I have a sum here of the square of something, so everything here is positive, and I can get an upper bound by forgetting that I'm summing only over primitive characters. Okay? So now let me bound this above by extending this to the sum over all characters chi mod q. Right? But now if I have a sum over all characters chi mod q of this sum, some guys twisted by the character value at b, I can use the orthogonality relations for all characters mod q. Okay? If I expand this out, I'll have two terms, chi of b1, chi bar of b2, summed over all the characters mod q, and the only thing that will survive is when b1 equals b2 mod q. So this will be just equal by orthogonality to phi of q, the number of characters mod q, times the sum over b mod q the sum of the squares of the exponential sums. Now let me make one more point here. When I'm summing these character values at b, right, I might as well assume that b is co-prime to q. If b is not co-prime to q, all of these character values are going to be 0. So in fact, the fractions that survive here are precisely the reduced fractions mod q. If b is not co-prime to q, it doesn't count at all. Okay? So far, so good? Now, at this stage, we are done because what I I can actually say is that, in fact, Q over phi of Q, which is always bigger than 1, times the sum over primitive characters mod Q, this is bounded above by the sum over coprime integers b mod Q, reduced residues of this type. And now I can sum this over all Q up to Q and use the additive form of the large sieve. So which by the large sieve is bounded by square. Right? So, in fact, if I go back here, what I've proved is stronger than the result that I wrote down here, because I also get to add for free this factor here, Q over phi of Q, which is always bigger than 1. It's making the bound that I prove stronger than the bound that I stated. That's good. Okay, so this is the form of the large sieve that we're going to find useful. So it's it's a good place to pause and see if you have any questions. The sum over here, right? So it's over n goes from 1 to n, if you like, right? Right. But remember, just as I said at the beginning of the lecture, that you can also imagine that your interval is shifted anywhere you want, from k plus 1 to k plus n, if you like. So the same thing would be true here, because at the end you'd have this exponential sum, and it doesn't matter where the interval starts from. The answer is not affected. So you could also make it k plus 1 to k plus n, if you like. Right? So that's a little non-obvious if you think of the character ones, right? Because you're shifting where the character starts. That's not easily, you cannot easily take a factor out, but the proof will tell you that it's true no matter where you start. Other questions? Okay, so let me make a summary. The large sieve is some kind of statement about, about expressing some average of something, right? So let me say the large sieve is average of something which I'm going to call some harmonics. This word has no meaning. It's just, it's just some placeholder for whatever it is that we've done, exponential, additive characters or multiplicative characters, right? What was important was that these harmonics were kind of different from each other. Yeah? The spacing condition accounts for it, or if you have characters, the two characters are different from each other, you have the primitivity condition guaranteeing that. And then the large sieve is some kind of bound which says that this is bounded by one worst case, where you can do nothing. One guy can be bad, and you cannot prevent one guy from being bad, plus square root cancellation on the rest. Okay? Or this is what you should shoot for. you should always shoot for something of the form 1 worst case plus square root on the rest. Maybe you will prove it, maybe you won't. Okay? But that's the flavor of the large sieve. And in this kind of generality, people have explored very many different situations in which you could prove what would be called a large sieve type inequality. Okay? And these inequalities eventually have nothing to do with the sieve, because we gave an application of the additive form of the large sieve for, as an actual sifting problem. But if you replace this by, these things being coefficients of some modular forms, and then you want to prove some estimate of this type, you don't necessarily have a sifting problem that you're thinking about there, but we still call all of those large sieve estimates. Okay? And maybe as an example of what kind of thing you could look at, you can, here's an exercise that you could think about. You can integrate, say, from 0 to t dt, right? So instead of varying additive characters or multiplicative characters, you could think of these guys, which are like quasi-characters. N to the it is a multiplicative function of n for any given value of t. If two different values of t are not close to each other, you would think that n to the it behaves differently from n to the y, let's say, if t and y are not close to each other. So here, the kind of inequality that you would like to prove, or even you can try to prove it as an asymptotic formula, that there's a result which would say that this is like t plus big O of n times the sum of mod a n squared. Okay. This is, I think I've written it slightly differently from the other ways I've done large sieve. The way you should think of it is that this t is giving you square root on average. This n is the one bad guy that can appear, right? Except in the discrete case, there's no one bad guy. If one guy is bad, there's a very small neighborhood around it which is bad. But it's a very small neighborhood. Okay. And you can think of, or you can try to formulate other examples where you might think some phenomenon like this is holding. Good. So now let's turn to the Bombieri-Vinogradov theorem. And I want to set up for the application of the large sieve, which will still take us maybe a lecture and a half or so. So let's recall that what I want to bound is something like the sum over q up to q, the max over a mod q. A is co-prime to q, and then something like the number of primes in the progression a mod q minus the expected main term, which is x over pq. Right? And in a suitable range of q, I want to show that this is no more than x divided by some suitable power of log x, which, for example, is what James used to bound some error terms today when describing how the sieve method works. Okay. Now, we want to get our hand on this object by using Dirichlet characters. Right? So by the orthogonality relation, I know that psi xqa would be equal to, so let's subtract out the main term, minus x over phi q. This is going to be bounded by the sum over all characters chi mod q, chi bar of a psi x chi minus this psi of x over phi q. I should just have said minus x over phi q, say, right? Okay. So recall that this psi x chi is the sum over n lambda n weighted with this character chi n. Okay. So if you plug that in here and use the orthogonality relation, you get 1 if n is congruent to a mod q, and you get 0 otherwise. Okay. So you can think of the term chi being the principal character here. Right? So there's always the principal character chi equals chi naught. The principal character here, chi bar of a, is just going to be 1 for the principal character. And psi x chi naught is just counting the von Mangold function up to x. Okay? There's a small issue with the primes that divide q, but let's not worry about that. That's really minor. Now that term will give you psi x over phi of q, and that's being subtracted from this main term here, which is x over phi q. Is that okay? Right? So if I really wanted to write this in a prettier form, maybe it would have been better to subtract psi x over phi of q here, so that it actually looks like an average, rather than putting in an x over phi of q, right? But it doesn't really matter, because you know the prime number theorem now, which tells you that this difference, you can save arbitrarily many power of logs that you want from x over phi q. Okay? And then if you sum 1 over phi q over all the moduli q going up to q, that just gives you 1 more log at the most. So you're still okay. You've saved arbitrarily many powers of log. Okay? So let's note here as an aside that this sum over q up to q, psi x minus x divided by phi of q, this is certainly very small. This is bounded by x over log x to any power a that I like. Okay? Here you have x over e to the c root log x for some suitable value c. Okay? Now what I want to bound is this quantity with taking the max over all a of this object. So what I can say is that the max over all a well, clearly this is bounded by just using the triangle inequality above, just taking absolute values everywhere. So it's bounded by 1 over phi q, the sum over all characters chi mod q, and I'm going to remove here the principal character. So the trivial character has been removed, and then psi x chi and then plus this other guy, which we just handled there, something like psi x minus x divided by phi of q. Okay? And this part, as I've just said, is harmless. I don't have to worry about it. So at this stage, what I want to bound is a sum over all q up to q, then a sum over all characters chi mod q, which are not principal, and then I have something like 1 over phi of q, and then the sum over the primes up to x weighted with this character chi m. Right? And again, I'm shooting for this to be bounded by x over log x to some power. This good? Okay. Now let's do one more cleanup, and then I'll stop. In this multiplicative formulation of the large sieve, you see that I was summing over primitive characters chi mod q rather than over all characters chi mod q, right? So as not to count the same character over and over again. Okay? So you can see that it would be helpful here also in setting up to use the large sieve if I had a sum here over primitive characters chi mod q rather than all characters chi mod q. So let's do that. So probably don't have too much to say, so I can just use this. So I want to restrict to primitive characters. Well, how can I do that? What I have here is a sum over, so suppose I summed over all primitive characters mod q, right? Then what I will be missing would be the character, if I have a primitive character mod q, I'll not be counting the ones which are induced by it, mod 2q, mod 3q, mod 4q, etc. Yeah? So what I want to count is a sum over q up to q. Let's assume that q is bigger than 1, so I'm not counting the trivial character at all. Okay? Then I'm going to count a sum over chi mod q. Now it's going to be primitive. Psi x chi. And then I should count it with an appropriate weight to think of all the imprimitive characters that are induced by this primitive character chi. Okay? So what are those imprimitive characters? Well, they will appear at the multiples of q. So it will be a sum over, let's say, r. So I'm going to think of the ones modulo q times r. What should r go up to? Well, q times r should be less than capital Q, so r goes up to q capital Q over q. And then what I'm counting here is the weight 1 over phi of q, right? So when it appears as a character mod qr, it will be counted with the weight 1 over phi of qr. Okay, so this here would be 1 over phi of qr. This is good. Okay. So now at this stage, let me just make a simplification here. Remember that on the first day you worked out that phi of n is roughly like n. It's at least like n over log n, and usually it's on the same scale as n. So, and in our Bombieri-Vinogradov theorem, we are going to save arbitrarily many powers of log, so I'm not going to worry about forgetting a few logs. So let me just think of this as QR and replace it by a log x throughout, right? In the rare cases when phi of QR happens to be smaller than QR itself. So this is bounded by, so this sum I can say is bounded by 1 over q, and then a sum over r goes up to this range, so it gives me another log of q. So maybe let me put a log of x squared here. Right? I've replaced phi of qr by qr, accepting one loss of a log, and then I sum the log 1 over r up in this range, accepting another loss of a log x. Yeah? So now we've tidied up what we want to sum. We want to estimate, so it remains to estimate so sum over q up to q, 1 over q, and now I have a sum over primitive characters chi mod q, and then psi x chi, and then I want to save, so I want that this is less than x over log x to the a. Okay? So I should really have said I want this to be less than x over log x to the a plus 2, so that when I give back this 2, it gives me Bombieri-Vinogradov in the way that I wrote it, right? But I'm just going to call a plus 2 as a in this step, to save arbitrarily many powers of log here. Okay, so let me stop here, and then I will continue on Monday, starting from here, and then showing that how the large sieve applies here. You can see that we are kind of setting up ourselves up nicely, but one thing that's missing is that the large sieve applies to give you things about the mean square of various quantities, and what we have here is the L1 norm of something rather than the L2 norm. So we want to pass from this to sums involving 2 objects rather than just one, and that's the additional ingredient that you need to complete the proof of Bombieri-Vinogradov. Okay, plus Siegel's theorem, which we'll come back to. All right. Questions? Yeah. Where this came from, right? It's just the same sum here, right? So there was always a 1 over phi of q here. So every time a character appears, it appears with this weight 1 over phi of q, right? Right? In the rewriting, I want to sum only over the primitive characters. So the primitive character will appear, but then also it will appear as 2 times that modulus, 3 times that modulus, and so on.
But then q and r may not be related with prime. So how will you combine?
So here it would have appeared as modulo chi modulo qr, psi x chi, being induced by this character mod q, with the weight 1 over phi of qr, right? So that's all I've written in that step, right? So from here to there is I claim an identity. Is that okay? The q's are different. So this one, I'm secretly thinking of this q as being qr. Yep. Okay. And then from here to this, I'm just going to replace that 1 over phi n is bounded by, say, log x divided by n. Right? Just, yeah. And then I don't have to worry about coprimality and so on. Yeah.
Can you say a little bit more about why the large sieve is equivalent to square root cancellation? It seems like we should get then just if we divide everything by q squared, which is the number of terms.
Mm-hmm.
Once we get the square root of q, that will expect.
So the trivial bound for S of chi, if you think of all the values of being of the same size, is n, right? Yeah. So the trivial bound for S of chi is n, and square root cancellation means that I should get terms of size square root n, right? So if I take S of chi squared, right, the bound should be n. If I get a bound of n, that's square root cancellation. So this q squared times the sum of mod a n squared, that's that square root cancellation. If you think of the a n's roughly of size 1, then that sum over n is capital N, and it's q squared times n, which is q squared times square root of n squared. Okay? And then the n squared would be the one bad guy.
What was the reason for this sum q less than big Q psi x minus x or big Q less than x log x to this arbitrary power?
Yeah. So what do you know about psi x minus x, right? The prime number theorem tells you that you get x over, that's bounded by x over log x to any power that you like, right? So then take away x over log x to an arbitrary power, and then you'd be summing 1 over phi q, q up to q, right? And that's like a log. That's all.
Why is it like a log x? Where's big Q again?
Big Q goes up to like root x, right? We would ideally like, so remember that the Bombieri-Vinogradov theorem tells you that there's cancellation up to a little bit before square root of x. And then, you know, other things like this Elliott-Halberstam conjecture would give you cancellation up to x to the 1 minus epsilon. So big Q goes up to, right? In any case, if you're thinking of primes and progressions, you don't want the modulus of your progression to be bigger than x. So it's always going to be less than x, right? So Q is some parameter less than x. So log Q I can bound by log x.
Okay, there's no further question. Let's sound again.
Okay.